All right, so section 4.1 is called antiderivatives, and in some way, shape, or form, this is going to be the opposite of doing a derivative. The first thing I'd like for you to do, though, on your paper, you guys know all of these, so I want you to jot them down, and then we'll fill it in together to make sure everybody doesn't have any details missing. I just want you to remember your derivative rules, okay? Some of these are very, very basic. In fact, most of them are. You don't see product rule, chain rule in here because that's not what we're headed into just right now. But go through here. I want you to write down what is the derivative of y equals b, what is the derivative of y equals ax plus b, and so forth. So x is your variable. All the other letters you're seeing, the b's, the a's, the k's, those are those are all constants. Those are all numbers. So write down underneath that column derivative what the derivative is of the function on the left. And you're welcome to go all the way down. This is two screens up here, but you're welcome to go all the way down with the derivatives, the entire front of your sheet if you'd like, down to the sines and cosines, the trig ones at the bottom. And then we'll do all of them together and fill them all in and make sure everybody has the details correct. Most of you are a good ways into this. Let's make sure that everybody has the details the same. What's the first one? What is the derivative of y equal b? 0. This is the derivative is 0. So I'm writing that notation, right? Y prime equals 0. How about the second one? What is the derivative of ax plus b? It's just the a, right? It's the, remember derivatives are slopes. The slope of that is a line, and that's the line with a slope of a. What happens when we have a constant multiplier? Can you help, Grace?
It's kf prime of x.
Right, so the k stays put. It just acts, like a coefficient. It is a coefficient. And then we take the derivative of the other piece. And since we don't know what that other piece right now is, we'll write it generically as f prime of x. Okay? What happens when we have a sum? We like sums and differences, right? Because what happens? Yeah, you just take them individually. There's no sort of interplay between them. So we'll do the derivative of the first one plus or minus the derivative of the second one, whichever the sign was between them to begin with. And how about the power rule? That's the only one on here that really has sort of some meat to it, where we're actually going to do something. What do we do when they do the power rule? All right, so we sort of bring down the exponent to the front as a multiplication factor, and then we decrease the exponent by 1. Everybody good with those? Yeah, you've been working with them for quite some time. Now, these over here they're a little bit harder to remember in pieces simply because we don't see them as frequently. They're not used on almost every single problem. But the first two are really easy. I know you know those. So let's do the first one. What's the derivative of sine? Cosine, you bet. And then what's the derivative of cosine? Negative sine. Those are the ones that I tend to remember real quick too. The other four are a little bit more complicated. What is the derivative of tangent? Secant squared is correct, yes. And the derivative of secant is? It has a secant in it. There's no squareds, though. Secant x times tangent x. Very good. So the derivative of secant is secant tangent. If you know these two, that is, if you know that the derivative of tangent and you know the derivative of secant, the next two are very, very similar to those in nature. So what is the derivative of cotangent? Right, it's cosecant squared, just like the tangent one is. So tangent became secant squared, cotangent becomes cosecant squared, and you see I left a space. Why? Because it's negative. And I know I've had a number of you in my office, and I've talked to you about this before too, that if you take a look, the ones that change signs are all of the ones that start out with co. Cosine becomes negative sine. Cotangent becomes negative cosecant, and we're about to do the last one. Cosecant becomes what? Yep, and it's negative as well. So this one's negative, and then it's cosecant x, cotangent x. Again, much like the secant derivative, right? So secant becomes secant tangent, cosecant becomes the negative, but then it's cosecant cotangent. I left a c out. Let me put that back in. There we go. Cosecant x, cotangent x. Okay, so you guys remember all those, right? You guys are feeding them to me pretty well. Some of the ones at the bottom are a little bit less well, but that's okay. What we're going to do is we're going to actually do the opposite now. So just a little bit of notation, a few things that you're going to see. Capital F is what's sometimes used as an antiderivative of small f. So if we have a function small f of x, which is usually how we're given a function, and we want to sort of give a notation for the antiderivative, they'll make it capital. The other thing that will sometimes happen is that they'll actually call the original function f prime, like they've already got the prime there, in which case they just call the original one f. They're just doing that sort of like a backward step on something. This is always done on an interval I, and it's called an indefinite integral of f with respect to x on the interval I. And then you see this notation. So right here you see this sort of funny script S looking thing. This is the integral notation, kind of like our derivative notation is the prime notation, right? Or the df dx notation, different things like that. Our integral notation looks like this symbol. And every time you see that symbol, you're going to see it associated with a d something at the end. That d something at the end identifies what the variable is. And that's why this right here said with respect to x. That's what that dx here in the end means. It means that no matter what's going on in the problem, they're identifying for you what the variable looks like. The variable in this problem is an x. Now your book tends to just use x's everywhere, but occasionally you'll see something using a t, because t is for time. So you'll see that occasionally. So they're just telling you here now, notice that this is saying the integral with respect to x of the function f of x is this capital F of x. And then you'll notice the other thing on the end here that's different now is we have this thing that says plus c. And here's why. What we're doing is we're sort of taking a step back and we're saying the graph that we're given is the graph of something like a slope. And I want to sort of revert back and see what the original graph looked like. The problem is that the graph can have the same slope no matter how high up or down it is. So for instance, let's say we started out with a graph capital F of x that looked like this. Okay, just a plain old kind of a cubic looking graph. My screen's not showing you all the details just yet, but this was the original graph. I did not mean for this to be capital. Let me change that to be just a lowercase f of x. No, I did. I meant for it to be capital. Sorry, I was thinking about which direction I wanted to go. If you take this graph and you compare it to this graph right here, had I drawn them well, so if I had drawn them well, they appear to be the same graph, just one's shifted up and down from the other one. Again, I know I didn't draw perfectly, but you got the idea, right? The kicker is that if you drew the derivative graph for this, it'd be the exact same thing, because at every x value it has the same slope. It's just got this sort of a shift going on, right? One's higher up along the y-axis than the other one. That's all that's different. That's exactly why this plus c is here at the end. It's recognizing that when we're finding the antiderivative, there may be a shift that we can't identify going on. So every time you do an indefinite integral or an antiderivative, you're going to put a plus c on the end. Okay? So you're going to see me do that on the next set of slides. So what we're going to do next is we're going to go through and we're going to identify the antiderivative rules. It will help to keep in mind or to have it next to you that derivative rules sheet that we just did. Because what we're wanting to do basically is we're wanting to start in the right-hand column and we're wanting to go backwards. Okay? So how in the world do you get a derivative of 0? What would have happened to cause that? You had a number to start with. So the original graph or the antiderivative would have been simply a number, and we'll call that number the c value. We have no idea what that number is, but whatever it was a horizontal tangent line, right? That's what became a slope of 0. I mean, it had a slope of 0, so the derivative was 0. The next one, and I just used the same notation that is usually used. I don't like that there's k's and c's in the same problem. They usually both mean constants, but we'll deal with it. Oh, and I want you to identify this as well. Let me make sure I note it. This should be a capital Y here, just like we did that capital F. So whatever it takes for you to recognize that you're doing a different function, it's not the same Y function you started with. All right, so what in the world, or how in the world did we get a derivative that was just a simple number, a non-zero number? We had an x in it, and a plain old x, right? Not squared or anything like that. Nothing fancy done to it, just a linear function. So we had k times x, right? That was the slope. And then we had some possibility of having an additional plus something on the end. We had a line. This is the equation of a line with slope of k. So its derivative, which is where we started, was k. Now the next one isn't actually the same rule, but it's very similar. What do you think is going to happen when we have a constant multiplier? Take a guess. Right. It'll very much mirror what we did on the other one with a constant multiplier. It'll still be the function's the constant there. The constant just stays because it's multiplied. And then we take the antiderivative of the other piece. So in this case, it was small f of x, so we're going to call it capital F of x. And lovely enough, what do you think is going to happen on the next one? Yeah, you do the antiderivative of each piece as well. So we're going to do capital F of x. We'll do that same plus or minus that is already there, and then capital G of x. So when we have addition or subtraction for derivatives or antiderivatives, the same process applies. You just do it piece by piece. Now the power rule is the first one that actually you need to think about with me, okay? Think about the power rule back for derivatives. What did we do when we had x to the n? Okay, so let me take the first word you just said. You used the word multiply. So the opposite of multiplication is division. We're going to do some division on this problem. And what did we multiply by, Brooks? Well, we multiplied the number to be in front of x, but what number was that originally? Like you showed it up down here, but where was that number originally? It was in the exponent. It was the original exponent, right? Okay. So the original exponent is where we sort of obtained this multiplication factor. What did we do to the original exponent next? We decreased it by 1. So what is the opposite of decreasing something by 1? Adding 1. All right, so the first thing we're going to do here is we're going to increase our exponent by 1. That's the opposite operation. The other thing that we're going to do is instead of dividing, which is what we just said we were going to do, the opposite of multiplication is division, instead of dividing by the original exponent, we're going to divide by the new exponent. So we end up with x to the n plus 1 divided by n plus 1. There's division instead of multiplication. We increase the exponent instead of decrease it, and we divide by the new power instead of the original power. Everything's the opposite. Does that make sense? And what's more is if you took the derivative of this, right, you would say n plus 1, I'll bring it down, which would then cancel with the denominator. And if you decreased that exponent by 1, you'd get n, which is exactly where you started. Now that I'm to here, let me go back and add something to each of the problems that I've left off. What have I left off? plus c. And I mean, we did it in the first two. We talked through that. But on each one of these, I don't quite have enough space on the second, or that last one right there, but it's sort of there. We have the ability to do plus c, because what's the derivative of the constant c? 0. It goes away if I were taking the derivative of it. So we have that sort of a possible shift going on with that plus c. All right, you ready to look at the trig ones? What do you notice in the trig ones that's a little different than the original list? Huh? There's no negatives right now, so we are going to have negatives in the anti-part. What else do you notice? Compare the original functions to the original functions on your other list. Are these the same? Is this the same list? You don't see tangent or secant or cosecant or cotangent. We'll get to them, but they're not nice and clean derivatives, antiderivatives. There's none of that going on. What you actually see right here is that with the exception of the negatives that Jamie listed, these are the derivatives from your previous list, aren't they? That's actually what you have here. You don't have the original functions rewritten down. You have the original derivatives with the exceptions of the negatives. So I want you to really think about, how would I get a derivative that's sine? What would I have had to have? What function has a derivative of sine? Yeah, cosine, and then what did you say, Brooks? It's negative, because the derivative of cosine changes signs, yeah, like as in positive, negative signs. How do you get a derivative that's cosine? It's sine, and it's positive, isn't it? Yeah. And let me go ahead and write these as we go. We'll put the plus c's on as we go. We recognize that all of these are going to have plus c's. So the derivative of sine is cosine. The derivative of negative cosine would be the opposite of that. So we would get positive sine, right? How in the world did I get a derivative of secant squared? Whose derivative is secant squared? That is tangent. And it's positive, right? No sign changes necessary, plus that c at the end. How did I get a derivative of secant x tangent x? That is secant. And then plus that constant at the end. And I haven't done a very good job. Hopefully you're doing a better job of making yours capital Y's. I don't write capital Y's very often, I guess, so I'll go back and make mine look capital. You'll see the function notation f of x used far more. I don't have as much difficulty for some reason writing a capital F as a capital Y. I don't know why. All right, the last two. Whose derivative was cosecant squared? Right, more or less we're talking cotangent here. But normally, if we're going the other direction when we were working with this before, the derivative of cotangent was negative cosecant. And just like Jamie said, that's missing. The negative's missing, which means that we need another negative involved here in order to be able to work with this. The derivative of cotangent is negative cosecant squared, which would then give me a negative to cancel out with this negative to give me the positive cosecant squared over here. And the last one, what was that one going to be? That one's negative cosecant of x plus c. Okay, you guys ready to practice some of these? So some of these are going to require a little bit of algebra as we work through them. Some of them won't. Some of them are very straightforward. All of the ones that we're going to do in your homework, you're going to simplify just like you did with your derivatives. Okay. When you do your basic skills quiz, you don't have to simplify anything, just like before. Okay. All the rules stay the same. All of the directions of what I'm doing stay the same. And all the rules are reversed that we just discussed, right? Okay, so there's a couple of things you could do. I see a 2x here. So one thing you could do is you could ask yourself, especially when it's a number like 2x, how in the world did I get a derivative of 2x? And the answer would have been that you had an original function that was x squared. So you might actually recognize this one as, oh, that would have had to have been x squared, because if I took the x squared and took the derivative, I'd get the 2x. Yes?
Did you already go over the cosecant x cotangent?
Mm-hmm. Right here at the bottom? Yep. It was the opposite of cosine, or cosecant. Yes. You got that one now? Okay, great. And the same is actually true. This is one that has the sum difference thing between them, so we're going to be able to do them in pieces, right? The same is actually true for 3x squared. So how in the world do you get a derivative that's 3x squared? It came from x cubed, right? And there may or may not have been an additional value that was a constant on here, because what would the derivative of c be? 0, and of course then it just sort of goes away. So we do that plus c on there at the end because there could have been a constant that was actually a portion of this. Now, if you didn't recognize that 2x became the x squared and that 3x cubed or squared was coming from x cubed, you'll appreciate the next problem so that you can identify that a little bit easier, because you don't have those sort of a telltale where I came from thing going on quite there. This one requires us to simplify the algebra a little bit. How else could I write 1 over x cubed, x to the 6th, which would be a little bit easier to work with these rules that we're working with? X to the negative 6, just like when we were doing derivatives, right? You need to have that dx every single time you have that script s. They go together. All right, you cannot have one without the other. These two pieces need to be on the same problem. Now, I'm going to do the derivative rules, and I'm actually going to, or the antiderivative rules, and I'm actually going to do it without saying, where did the x to the negative 6 come from, which is kind of how I used my phrasing on the last one. This antiderivative rule is the power rule. I've got x to a power, right? I need to increase that power by 1. If I increase negative 6 by 1, what do I get? Negative 5. So the new power will be negative 5, and then I divide by the new power. This piece right here is just a constant. Now, when you take a derivative of a constant, it goes away. When you take an antiderivative of a constant, what happens? You attach an x to it. So the negative 2 becomes negative 2x. That's probably the trickiest thing to just remember, because we're so used to seeing a constant and it just going away. When we see a constant now, we reattach an x to it, multiply it by x. And then we've got the plus c there on the end. Now, just like before, if the problem did not originally start out with negative exponent, it's not going to end that way either. It can on your skills quiz, but and nowhere else. So since this originally started out with positive exponent in the denominator, we're going to take this exponent and we're going to bring it back down to the denominator. So this is actually going to look like 1 over, the negative 5 is already there, x to the 5th will now be there as well, minus the 2x plus c. Does that make sense? It sort of feels like we've just turned the tables. It should, because as we did, we just changed all the rules. You guys ready to try another one? All right, this one has a square root in it, which there was definitely no square roots in any of those rules that I used. What do we have to do when there's a square root involved? What do we do with derivatives when there's square roots involved? We use the exponent of 1/2, right? So in some sense over here, what we really have is we have an exponent of 1 and an exponent of 1/2. And what do exponent rules say that I can do then? What's that? Add them together, you're right. So I can rewrite this as x to the negative, it's a negative exponent because it was in the denominator originally, negative 3/2. You see that dx coming into play again. Never disappears until the script s, until you've actually taken the antiderivative. Okay, is everybody good with that rewrite first? Okay, great. This is just another power rule, right? I have to take that exponent negative 3/2 and I have to increase it by 1. So what do I get when I increase that exponent by 1? Negative 1/2. And I divide by the new exponent, negative 1/2, which looks really odd because now I've got division by a fraction. What am I missing? Not yet. I don't have the dx anymore because I took the antiderivative, but I am missing the plus c, right? Skills quiz, you can leave that. Homework and everything else, we're not going to. Let me deal with the fact that we're dividing by the negative 1/2 first. What is the same thing as division by 1/2, or negative 1/2 in this case? multiplying by, in this case, -2, right, Zach? Yeah. So this is actually the same as having -2 and then the x to the -1/2. So that 2 will not be in the denominator. It is a constant multiplier of -2 to the whole function now. But this exponent being negative will put that x back in the denominator. So I have an x, or I've got an x in the denominator that's got a power of 1/2. But the original problem didn't start out with powers. We introduced that notation. So how will I write the final answer in terms of the original problem? Right. -2 over the square root of x plus c. Is everybody okay with that last step? We brought this down. It's got an x to the 1/2 in the denominator. And then because it was a 1/2 exponent, that's giving me back my square root. Here's the cool thing about doing these. Now, you're probably not going to do it because it's just one more step. The cool thing about doing these is you can know that you did the problem right if you choose to on every single one. How could you do that? You could take the derivative of your answer. If you take the derivative of this answer and this answer is the correct answer, you will get the original function that you started with inside of that notation. Every single time. You don't need it back of the book. So even if I've signed you even problems, and you know I always do sign some of those, right? You can always check to make sure, if you really want to, that you got the right answer by doing that. What are we going to do on number 4? What's that? It is a product. We don't have a product rule. Nope, it isn't, because it isn't a constant multiplier, because we have variables in both pieces. We need to FOIL it out, absolutely. In fact, even worse is that, just kind of I will break the tension in the room saying, is there a product rule? There's not. There is not a product rule for antiderivatives. Products, when you have antiderivatives, are really difficult to work with, and you're going to have a series of different kinds of rules, and we won't even finish it in Calc 1, because that's where Calc 2 starts, is with all of the different things that can happen when it looks like products are involved. So we want to eliminate the fact that it looks like there's a product, and we can do that by doing foiling or distributing this thing out. So that is how we're going to start this problem. So I'm going to rewrite this, and I'm going to FOIL it out. So x times 3x is 3x squared. The outer terms give me -2x. The inner terms give me positive 3x. And then the last terms give me -2. And don't forget the dx on the end. You could take this right here and do the antiderivative. That would be fine. But you could also recognize, you'll have to simplify it later, but you could also recognize at this point that these two combine, right? So that's what I'm going to do, is I'm going to go ahead and combine those before I do the other part. So this is 3x squared plus x minus 2 dx. And your book, I don't think I saw this quite so much in here, but I'll just let you know. Some books are real specific. Some resources are real specific. They'll keep things in parentheses when there's any additions or subtractions in them. I'm not going to be particular about that, so put them in there or don't put them in there. I don't care. They're fine without it. 3x squared. What's the antiderivative of 3x squared? That is x cubed. If you want, you can use the product or the power rule, right? You can take that x to the 2, increase it by 1, which would be x cubed, and then divide by 3. Then you'll notice that the 3 at the front and the 3 divided by cancel to give you x cubed. If you happen to recognize it, as many of you did, you can simply write the x cubed down. That's fine as well. What are we going to do with the x? Right, so that actually has an exponent of 1, right, Zach? So we have to increase that exponent by 1, which would be giving me x squared. And we divide by the new exponent, which is a 2. So you can either write that as x squared over 2, or you could write it as a 1/2 times x squared. What are we going to do with that minus 2? We're going to what? Okay, you don't really mean add, right? Attach or multiply by an x, right? Yes. So we're talking about including it being multiplied by x. And then we are going to actually add something. We're going to add a c. So you could leave this written like this, or you might write it as x cubed plus 1/2 x squared, which would be fine, minus the 2x plus c. Either of those would be perfectly fine. Any questions on that one? Okay, a couple more, and these, of course, have your wonderful trig information in them. But they're not all trig, so we want to be a little bit careful. The first piece here says I want the integral of the number 1. So what is the integral of the number 1? It's x. Right? Just like on the last one when we had that 2, we attach an x to it or we multiply it by x. If it helps you to see this, you can write this as 1x down. That's what you're really doing. You're multiplying that 1 by x. Now, what is the antiderivative of negative cosecant x cotangent x? Right, so it's already got one negative here. So we can write the negative we'd like, and then the antiderivative would actually be negative cosecant. Whoops, what am I seeing there? We still need a plus c. Or if you happen to recognize the negative was already there, that would have been fine as well. And you can recognize then that this is x plus the cosecant of x, either originally or when you simplify is fine, plus your c. Because the derivative of cosecant x is negative cosecant x cotangent x, right? That's one of your rules thought of in reverse. Now, number 6 looks like it'd be awfully tempting to do some sort of division. That is absolutely not helpful here at all because the denominator has addition and subtraction in it, so we can't simplify that way. But you can simplify something else in that denominator. What else could you do with that denominator to simplify this problem? It is cosine squared x. Very good. That's the Pythagorean identity. Sine squared plus cosine squared equals 1. So 1 minus sine squared is cosine squared. So you might want to brush up if you're a little bit rusty on those trig identities, because they are going to be useful at different points here. Now, because this says cosine squared, what I'm going to do may not be sort of what you would have thought to do next. It might be. But I'm actually going to write it as cosine twice. Cosine squared means cosine times cosine. So I'm actually going to write this as sine x, over cosine x, and then 1 over cosine x. Why might that be helpful? Okay, and? Yes, it is. And I have a rule for that, right? I mean, I have an antiderivative rule that we have discussed. What is the antiderivative of tangent x secant x, or secant x tangent x is how we usually write it. It's secant x. And you want to remember what? Plus c.